Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were looking at the nature of the cosmos, how it grew from such forth, and we elucidated an incredibly important thing, how the Big Bang works in the standard Big Bang model. We looked at the hot Big Bang, we looked at how it expands with time, but now we're going to actually see some important elements to it, meaning what happens in the earliest moments. We know that the universe has been expanding since it expanded yesterday, so it'll expand again tomorrow, which is kind of a tautology, but hey, here we go. What we find is that the earliest moments we have incredible amounts of information about. Without the knowledge of the abundances of chemical elements in distant and ancient stars, we wouldn't really believe it. But there's some problems. So let's actually go take a look and see what they are. And find this kind of shows what we're going to be looking at, which is the cosmic microwave background we've seen. Then we have this weird epoch we can see in this cartoon called the Inflationary Epoch. We also can see this strange little thing called a quantum gravity era. We'll see what that means in this lecture. All right, so the successes of the standard hot Big Bang model, which was the idea of the primeval fireball of the cosmos, has a number of major successes, and all of them are observational. The first is that galaxies and quasars and supernovae at redshifts less than about 6 tell us, which means that this is since a billion years after the birth of the cosmos, or the last 12 billion years. They can tell us about the universe at later times. So we really do understand how things evolve, and that time since about a billion years after the Big Bang tells us a lot. And so that's also part of it, is the evolution of the universe since that part. The cosmic microwave background tells us what was happening right around 300 when the universe was about 350,000 years old, and it was a key prediction of the Big Bang at a redshift of about 1100. And so then we also look at the abundances of light elements, such as deuterium and helium, in the intergalactic medium, as well as in the presence of ancient stars. Not deuterium in ancient stars, but definitely intergalactic media that absorbs light at deuterium wavelengths at different redshifts. And so we can get deuterium abundances throughout the cosmos, and the predictions from that are and what we see from that is actually predicted by the Big Bang nucleosynthesis, as we saw from the measurements of the WMAP probe and the Planck probe. And so that gets us to a redshift of about 300 million, and when the universe was only about 3 minutes old. So we actually know pretty much, without getting into general relativity or anything like that, except for the expansion of the universe, and also just some assumptions about the nature of the universe, that it's isotropic and homogeneous, and that it's expanding. If we start from that, that's all we need in order to predict pretty much everything we've seen. So that's classical physics all the way down. And even then, we can look at how much, what the primordial gas clouds give us, how much helium and hydrogen are in the cosmos. The ratio of hydrogen to helium tells us what happened at roughly the time of neutron-proton freeze-out, meaning when neutrons and protons were in balance. And that's about when the universe was 1 second old. And that's about a redshift of 4 billion. But the freeze-out time when neutrons and protons were out of balance happened about 1 second. So we pretty much can answer almost every aspect of the cosmos observationally down to about 1 second after the Big Bang, which is an amazing triumph. But that amazing triumph has some problems, and there are 3 problems that occur with the standard hot Big Bang model. The first is called the flatness problem, and it can be stated that the universe is nearly flat today and therefore must have been even flatter in the past, because gravity works. And since gravity works, it deflattens things. The Earth is kind of lumpy, galaxies are lumpy, galaxy clusters are lumpy. So we're looking at the largest size scales, and on the largest size scales, it's pretty flat. So lumps do not extend to the entire cosmos in terms of size scales. So the universe is nearly flat today on the largest size scales, and even flatter in the past. The horizon problem states that the universe is isotropic and homogeneous today. Wait a second, that's what we've been using as an advantage. Uh-oh, now it's a problem? And so it was even more isotropic and more homogeneous in the past, which is really quite scary. Before, we've been looking at that as a bonus, as an intellectual starting point, as a touchstone, and now we're calling it a problem. Finally, there's the monopole problem, which says the universe has no magnetic monopoles. Well, okay, that's a little weird one. Maybe there weren't any to begin with, but we'll just start with it as a concept. So this is something arises out of particle physics. All right, so here we go. And the first one is we call it the flatness problem. Today, the critical density, or the density of the universe compared to the critical density, is almost equal. The universe is almost perfectly equal to the critical density for the cosmos, meaning bound right between an open and closed universe in terms of geometry. If it is not perfectly flat, it is really close to it. But the universe expands, the universe only expands, and the universe only gets farther and farther away from flatness, as we can see from combining the two equations. So we have the equation that governs the Hubble time, which is the upper left equation. Actually, the omega as a function of time on the left, 1 minus that. If it is going to be perfectly flat, that would be equal to 0, so that kappa is 0. So if kappa is not 0, say it is +1 or -1, and it is not a perfectly flat universe, meaning kappa is not by definition 0, but let's just say it's got some tiny amount of curvature. That tiny amount of curvature grows with time, and only grows with time. So there's many ways for it to be curved and only one way for it to be flat. So let's assume for just a moment that it isn't flat, that it's tiny, that it's very, very close to unflat. Maybe it's an open cosmos, maybe it's a closed cosmos. So let's see what happens. So if it's a closed or open, then kappa, that k, is not equal to 0. It's either equal to +1 or -1. C squared is the speed of light squared. R is the radius of curvature of the universe, or the scale factor associated with that radius of curvature. A is the scale factor of the universe, meaning how big the universe and how fast it grows with time. And the Hubble H parameter is how the rate of change of that of the scale factor grows with time. And on the right-hand side in the top right shows the current value for today. So if the current value for today is where omega naught, which is the current density of the universe compared to the critical density, if that's equal to 1, then somehow R naught and H naught combined with the C squared are really small, meaning the radius of curvature must be extraordinarily large, because h naught we know is like 70 or so, 67 kilometers per second per megaparsec. C is a number, which is 300,000 kilometers per second. So R naught has R sub naught, the radius of curvature, or the scale size of the lumpiness of the universe, has to be extraordinarily large in order to compensate for those things. So the middle equation shows how things evolve with time, and if we ignore for now the curvature, curvature contribution, omega sub k, and dark energy contribution in the early universe, and in fact we can eliminate it for now. We can just put that away for just now, and look at times prior to say 6 billion the first say billion years of the universe. Dark energy is a tiny contribution. Curvature wouldn't be that big a contribution, but we know that radiation and matter would be the big things. And so we can eliminate those two things out of what constitutes the Hubble parameter and get the equation at the bottom. So if we then say what is the Hubble parameter as a function of the scale factor, we plug that middle equation with the two pieces lopped off into the upper left equation, and then just simply take those two that are above now and equate them. We find that no matter what, the scale factor grows. Currently, we define the scale factor of today as 1, so A of today is 1. So therefore, A of ago is less than 1 and smaller. So no matter what, that thing grows. So 1 minus omega as a function of time, meaning the scale, the density, energy density of the universe compared to the critical density, that veers away from the critical density as a function of time. So no matter what, it gets bigger. Flatness goes away. And no matter what, it always gets more and more and more lumpy with time. So for today, then we just go take that last equation and say, for it to be 1 today, then as we look back in time, A gets smaller and smaller, gets closer and closer to 0. It's always between 0 and 1. So it's always some tiny fraction of that. So it gets bad And by how bad, we mean bad. If we go back to the time when radiation and matter had equal amounts of energy density, which is about 50,000 years after the Big Bang, we find that's a redshift, then it has to be the omega sub t has to be 1 to within 1 part in 10,000. If we then go back to Z, which is a redshift of 3750, that means the scale, which is when this would be, the scale factor is really tiny, which is like three hundredths of 1%. So that's really small. So that's roughly 1 in 10,000. If we go back and further in time still, and we go back till the time of nucleosynthesis, when the universe was 3 minutes old, then the difference has to be, then the scale factor now is really small. The universe is incredibly tiny at about 3.6 times 10 to the minus 8. So it's that much smaller, or 60 trillion times smaller than it is today, which is astonishing. So the scale factor, the universe was more than 1 billion times smaller than it is today, more than 30 billion times smaller than it is today. And therefore, it has to be really smooth at that time, such that as it grew to today, it is still close to 1. If we then go back to the earliest possible time that we can possibly think of, which would be the Planck time, which we'll discuss later, then that would mean about 1 part in 10 to the 60th. So to get some ideas of what we really mean by that, the first thing, radiation matter inequality, it's another way of saying it is that imagine you have 10,000 people. This is the radiation matter inequality. So everything's the same except one. So it's the old game from Sesame Street, which of these things is not like the others? And imagine you have 10,000 people all go to one place. Maybe there's 10,000 people all going to okay, so they all go to a big concert or something. There's 10,000 people at the concert, and every one of them is exactly the same height, exactly the same. Maybe they're all women. They're all wearing the exact same dress, the exact same dress color, the same hem length. They're all the same height. They all the same hair. They all the same everything. Everything's the same, down to their purses, down to the shoes they wear. Everything except one of them is wearing a flower in her hair. And that's the only difference. So that's how rare that would be. It was like, oh, one person's different. The next one, with thermonucleosynthesis, is effectively, now think about it this way, to have it be the same as in 1 in 33 to 3.3 times 10 to the 14th. So now imagine there's 10 billion people on Earth, and they're all exactly alike. And then imagine there's 33,333 Earths, all with 10 billion peoples, all identical, all except one. That's kind of scary. There's 10 billion people, so pretend, so there's roughly 10 billion people on the Earth, and for some reason, some crazy alien comes along and makes everybody exactly alike. And then he does that to 33,000 Earths, 33,333 Earths. Each of those Earths having 10 billion people. So they're pretty busy aliens making everybody exactly alike. But somebody dodges the alikeness ray, 1 out of 33 times 10 to the 14th. So the last part, the Planck time, is even weirder because to have 1 part different in 10 to the 60th is a really strange thought. We can just think that the sun has roughly 10 to the 60th electrons. The sun is a big star. It's made up of a lot of stuff. And it has maybe 10 to the 60th electrons. For it to be perfect to what, let's say, the difference is, take away or add or take away 1 or 2 electrons from the sun and say, oh, we've noticed that difference. That's the differences we're talking about. Like, take away 1 electron out of the sun, and the sun is 10 to the 60th electrons. So it's kind of a wild thought. So what does that effect have? The effect is that if the density parameter is not fixed, if it's not really close to 1, and doesn't matter how tiny that difference is, that as time progresses, so the Big Bang is to the lower left of that graph, as time progresses, stuff's going to happen. So you can have an accelerating universe where all of a sudden, oop, I've got less stuff than I need, and all of a sudden the universe accelerates, or it's got more stuff and it closes, and maybe it's a critical density universe and there's only matter in it, or maybe it's an open universe and it is just not just matter, but maybe radiation and dark energy, and we have the other one. So you have all these different paths based on what the universe is made up of. But down at the Big Bang, at the very beginning, they're almost completely identical, except for maybe one electron less or more in the sun worth of difference. And then that, as time goes on, differentiates them between the various paths in the future. So Big Bang is time equals 0 in the lower left, and as time goes on, the tiniest differences that become larger and larger and larger. It's much the same way as thinking about, saying, trying to balance a pencil point on its tip. So if you take a pencil point and balance it on its point, it has to be perfectly balanced. So imagine that you've perfectly balanced a pencil point on its tip and it doesn't fall over for 13.8 billion years. The longest possible time that any reasonable person can make this this pencil balance. And you can try this if you get really bored at work, right? Just like I did. So you can try this, and you'll find that it takes the longest it'll stay up is half a second at the last. But imagine you balanced it perfectly, so incredibly perfectly, it still hasn't fallen over after 13.8 billion years. That's the equivalent of the flatness problem. All right. So yeah, that's going to be kind of a tricky one. Yeah, that's a hard one to do. Okay, so here we go. That's the flatness problem. If it's not, it was flat ago, and if it wasn't flat, it would the end result would be a closed universe. It would collapse on itself, or it would be an open universe and it would accelerate away. So there had to have been really close to flat at the beginning in order for one of those two things not to have happened to give us the universe that we see today. All right, next is the horizon problem. Well, first and foremost, we stated that the universe is homogeneous and isotropic on all of the size scales. Apparently, this is a problem because, what the cosmic microwave background map shows is that no matter which way we look in the sky, the universe has the same temperature. Meaning, if you measure the black body spectrum of any patch of the sky, it can be characterized by a 3 Kelvin background black body. And we got that by saying the following. We assumed the first law of thermodynamics, and when we look back in time, we said, oh, we assumed that the first law of thermodynamics applied, and that the universe was thermalized, meaning that everything in the universe was at the same temperature, and nothing could enter the universe, and nothing could leave the universe, and heat can't come into the universe, and heat can't leave the universe. So everything that's in there, including all the heat and all the energy, is part of the universe from the very, very, very beginning. So if that's the case, then it should all be at the same temperature. If it's all the same temperature, then it all has the same black body spectrum. And that was the idea behind the Big Bang. However, this ends up being a problem. Why? Let's look closely. The horizon problem says that, well, at 2 points across the sky, 2 points completely across the sky, A and B, the light is only getting to us now, which means that in order for A and B to have been in contact, the light is arriving now at where we are from diametrically opposed places in the sky. That's the first time the light has ever had a chance to interact. That's their first chance. Otherwise, we would see something different. So the light took about 13, I hate this 15, it's just an old dumb thing. 13.8 billion years to get to us from here, and 13.8 billion years to get to us from there. And we're seeing it first for the first time, just like this. So we see everything from every direction at a 3000 Kelvin gas. That's what we see the temperature being. And each of these patches are just getting to us now. That light is only getting to us now, which means that light has only had the chance to mix, to influence itself, to have that light influence any other particle at that moment. So in direct opposition to each other, they're the same temperature. So how could they do that if they weren't in contact? Because in order for there to be thermal mixing, remember the idea was that they have to be all at the same temperature. In order for everything to be at the same temperature, the light has to be in a dense area where it can't get out. The light can interact with, say, the electrons and protons, and then the protons and electrons can interact with the light, and everything becomes the same temperature, the light and the matter. However, if this is the first time the light is interacting with matter since it left there, then how do these two things across the sky have the same temperature? This is the first time they've had a chance to interact. And it's 13.8 billion years later? That's a problem. In fact, it's a big problem because this patch is also out of contact, Which is, okay, it turns out that those two patches right next to each other on the right-hand side are out of contact. And it gets worse. Every single one of these patches is out of contact. So basically, everything's out of contact. There's almost nothing that is in contact. And if we then get all the way over to here, we look at the cosmic microwave background, then all of these patches on the sky that are about the size of the red dots are out of contact with each other at the time that the cosmic microwave background radiation was formed. So each of these dots, and there are about 200,000 such patches across the sky, because each patch is about a degree in sky. So any patch that's more than 2 degrees away, more than a degree away from something else in the sky on the cosmic microwave background, has never had a chance in the past to actually thermalize with the patch 1 degree away from it in the sky. So therefore, there's 200,000 independent patches in the sky. Whoops. Now that's kind of weird. How do you get 200,000 patches in the sky to have exactly the same temperature when they never had a chance to be in the same context? So it's like, you can basically, another way to look at it is you're all going to a potluck party, and or I liken it this way: everyone is going to meet at Times Square for New Year's Eve, and so New Year's Eve, Times Square comes along, and then 200,000 people choose to go to Times Square. When do they choose to go to Times Square? They choose to go at noon on December 31st. Let's say nobody is going, nobody's chosen. They've all been given magic tickets, or actually, let's put it this way: nobody knows that they can go. And all of a sudden, you get a magic ticket that says you can go. So 200,000 people across the world are chosen at random to go to the Times Square on New Year's Eve. And so they have 12 hours to get there. And so they run. Now imagine that when everybody arrives, they are the same appearance, they're the same height, they're the same sex, they wear the same clothes, they all have the same funny green hat, they all have the same funny everything. Some people, though, are coming from Dubai, some people are coming from Rio de Janeiro, some people are coming from Brooklyn, some people are coming from Helsinki, some people are coming from Toronto, a lot of people apparently are coming from China, maybe even the hinterlands of China. Some people are coming from India, a lot of people are coming from India, and a few people, of course, coming from Togo, wherever we're coming from. But all of these people, no matter where they come from, are exactly the same appearance, exactly the same clothing, exactly the same height, build, everything, except for one person. They're all the same. That's wild. Actually, there's no difference. There's 200,000 people that arrive in 12 hours without having a chance to talk to each other to figure out what you should wear. Because they didn't tell you what to wear. You said, you can come. So how do they get all the same clothes? How do they get the same bags? How do they get everything? Nobody knows, because there's no way for them to interact inside the time frame from when they got the ticket to when they arrived at Times Square for them to actually know. And that's the horizon problem. There was no time for the light and matter to get to the same temperature before then. All right, next we have what's called the monopole problem, which is a weird one because it's one of the predictions of grand unified theories, is that the universe undergoes some sort of crazy phase transition as it drops below some incredibly high temperature. And that's kind of like freezing water or something like that. So the major phase transition occurred when you have this question mark time at the time roughly equal to zero, and then you have a time when there was like gravity was interacting with gravity, and all the other forces such as the strong, weak, and electromagnetic forces were all one, and then they broke apart. And that break apart then would cause strange things. So that goes from a symmetric state to a non-symmetric state, where the grand unified theories, the strong, weak, and electromagnetic forces were all one, and then they break away from gravity, and that creates a phase transition. And when that does, there will be strange appearances throughout the universe. And it's as though it's kind of like it is a phase transition, and it is a spontaneous loss of symmetry when the temperature is lowered. So just like water, what you have with water is that when it cools down, ice crystals form. And so it goes from being a symmetric thing inside of water, where all the water molecules can be oriented any which way. So that's symmetric. You have no idea which way they are formed. So symmetry has a certain sense of chaos, but it's also and disorder. but yet it also has symmetry, meaning there's no way to tell there's no preferred orientation in a liquid water except for, say, up and down. But if you put the drop out in space, then there's no up or down to water, so there's no preferred orientation. As soon as you cool it, though, ice crystals form. And when the ice crystals form, there are preferred directions along the crystals of the ice, or at least something that shows you a symmetry, that shows you a new asymmetry. And that's what we can see here is the idea that when ice crystals form, they form and create non-symmetries. Notice how water as a droplet is the same no matter which way you look at the drop. But ice crystals look different no matter from different ways of different viewpoints. So that means they are asymmetric, and water drops are symmetric. Now the other thing we can remember is that as ice crystals form, they actually stay at the same temperature as the water around them. So there is a binding heat that says or that must be released in order for it to create the solid known as water. So it can't get any colder until the liquid state of symmetry is lost and becomes asymmetric, and that releases heat going from a state of symmetry to asymmetry. So there's heat involved in this phase transition of organization. So then we can say that the monopole problem says that there would be a lot of magnetic monopoles, meaning strange places. Let's go back a second. So we have points on this. So there are places where the rods intersect, and there are places where the walls intersect of these crystals. And so you can have all sorts of crazy defects inside of ice. So we can make an analogy to say there will be domain walls where big pieces of ice push against each other as they're forming out of water. We can have line-like defects where two walls intersect, and then we can have point-like defects where many of these things intersect into a point. And the point-like defects are what we call the monopoles. So magnetic monopoles, then, are when these point-like defects would occur throughout the cosmos. And this would happen during the phase transition from the theory of everything, or TOE time, to the grand unified theory, or GUT time, when gravity broke away from the other forces. So that would be where the magnetic monopoles would have occurred. Strangely enough, it should have made a heck of a lot of them, like an enormous number of them, like 10 to the 87th of them. So that's because there's a huge amount of energy that would have been created during this phase transition. We do know that as everything breaks up, as asymmetries are broken, it can release an enormous amount of heat when you go from one phase to another. And so that phase transition can release heat in the form of particles. And so the particles can be created out of that heat, out of that energy. So the expected particles are magnetic monopoles, and the idea is that there's 10 to the 87th of them. Assume that this idea is correct, that the forces are all together and that they actually do this thing, then something like the monopole problem is occurring in the standard model of particle physics, but it only happens during the time of the universe, when the universe was 10 to the minus 43 seconds old, till when it was 10 to the minus 36 seconds old. And it goes from a temperature of extraordinarily high 10 to the 32nd Kelvin down to 10 to the 28th Kelvin. My goodness, it's cooler, right? It's a cold day as it drops by a factor of 10,000. The total energy per particle goes from 10 to the 16th tera electron volts to 10 to the a trillion tera electron volts. Once it cools off down to about 10 to the 16th Kelvin, and at about a trillionth of a second later, that's when the electroweak and electromagnetic forces break apart from each other and separate from the strong nuclear force. So the grand unified, so there's some very strange things that occur in the first between 10 to the minus 43rd seconds and 10 to the minus 36 seconds of the cosmos. And that would be when these strange effects like domain walls or cosmic strings or magnetic monopoles would have formed as a result of the phase transition of the early universe. So let's actually kind of look at what we are. That's a lot of words. Let's see what we meant by that. So the fundamental forces of nature, there are four. And the first one is the electromagnetic force, or the photons. And it's a long-range force because a photon is a particle of light, and it's radiative energy, so it can impart energy from here to there from radiation. And it's incredibly strong compared to gravity because you can levitate things with electromagnetic force. Meaning, have you ever seen people pick stuff up with a magnet? Yeah, you can pick up a paper clip with a magnet. So if you can pick up a paper clip, it's very strong compared to gravity. So you can pick it up. The strong nuclear force, which is bound by the gluons, is even stronger than the electromagnetic force because we know that protons can exist inside a nucleus, so they have to be that force has to be stronger. But yet it only acts on a very tiny range, 10 to the minus 15th meter. That's the only time range that it works on. The weak nuclear force, though, is not as strong as either of the other two, and its range is even smaller in terms of its interaction. And that's why we think in terms of the neutrino, because the neutrino is still something that is the force carrier for the weak nuclear force of the W's and Z's. And so the neutrino is indicative of the weak nuclear force interaction. So gravity is not shown in here because it's the weakest force of nature, so we only have four forces that accelerate particles that can cause the Newton's F equals ma. So only the strong nuclear force, weak nuclear force, gravity, and electromagnetic force exist in nature, and those are the only things that can provide an F to F equals ma. Everything else that we've ever heard of that makes a force on something is some derivative there too, with the vast majority of them being either gravity or the electromagnetic force. We really don't encounter the strong and weak nuclear force in daily lives at all. But if we go back in time, to a time when the universe was only 10 to the minus 15 seconds old, we get to what's called the electroweak force. The electroweak force is when the photons and the weak nuclear force basically are at high enough energies you can't tell them apart. And this earned a couple people of New York the Nobel Prize for realizing this and dealing with the math and understanding that this is actually true, that they actually they're the manifesting of the same thing, but you have to have extraordinarily high energies and high densities and over short periods of time. And when you actually look at extremely high densities, temperatures above 10 to the 15th Kelvin, then you can't tell the difference between light and the weak nuclear force. They're the same thing, which is a very strange thought that light can be the same thing as those things. It becomes one force, the electroweak force. And that's what we mean by a unification of the forces, is that these two things become the same thing in the same sense that you have what is the difference between steam and water? Well, at the very boundary between water and steam, at the right temperature and right pressure, there's almost no boundary that molecules can go back and forth between water and steam if the temperature is right and the pressure is right. And they just can go, oh, now I'm steam, and I get close to this area, but now I'm water, but now I'm steam, but now I'm water. So at the boundary area, there's no difference. It doesn't take any energy to go back and forth between them. And that's what we mean by the electroweak force unification. You can still have these two objects, but they actually act as one, meaning steam and water act as one under certain pressure and differences. Same with the electroweak force. Now we can theorize that there is a grand unified theory that says that at some point that the strong nuclear force binds into the electroweak force at much, much, much higher temperatures and higher pressures and higher densities, so that it becomes one force. We left out gravity, though. There's no experimental basis for the grand unified theory yet, but people make up stuff and they try their best. But it's going to be very difficult to actually find these things because it's very hard to isolate a gluon, which is the mediator of the strong nuclear force. So at this point, the grand unified theories are not experimentally verified. They're just a theoretical way of saying, well, they should get balanced as they get closer together at higher temperatures. But then we say, fine, let's extend that one more time. Gravity itself is thought to unify because all forces, things that make things do forces, it's thought to unify with the grand unified force at even higher energies. That's a pretty big maybe, though, because now you have to have, because there are theories of the grand unified theory concept. There are numbers where you can go the quantum chromodynamics and quantum electrodynamics get you there. But the nature of the grand unified theories don't yet include a quantum theory of gravity. So quantum theory of gravities are not exactly ready for prime time. People posit that there must be something called a graviton, or a particle that is a particle of gravity, which is a very weird concept. So let's just think that that's an odd thought to think what a graviton is, because there are two big camps on what exactly is gravity. General relativity says it's the shape of space-time itself, but particle physicists call it a force that is carried by a particle. So there is some, and so far, experiments have only been able to confirm the theory of relativity as the description for space-time. And the attempt to discover space-time quantum foam effects has been made more difficult because the Fermi Gamma Ray Telescope has looked at the arrival times of high energy and low energy gamma rays, which should have felt the effect of quantum foam effects or tiny bubbly gravity effects over a course of 10 billion year travel across the cosmos, and they don't see it. So gravity as unified with the strong nuclear force, weak nuclear force, and photons into one theory of everything, one force of everything, it's not well known. So there is at this point there is no quantum theory of gravity, and people are hunting for it because that would be really cool and it would be a big help, but there isn't one yet. So next what we say is that, fine, let's assume that we can get a quantum theory of gravity. So at the Planck epoch, we don't start anything at zero. So we're not going to start our time thinking at zero because we want to do physics, not metaphysics. We can't really say anything meaningful about time equals zero, but we're going to start our moment at 10 to the minus 43rd seconds. And this is right after the Big Bang, time equals zero. Well, 10 to the minus 43rd seconds is effectively time equals zero, but there's a lot of time between 0 and 10 to the minus 43rd. There's 10 to the minus 43rd seconds. A lot of things can happen inside that time, apparently, because a lot of things apparently did, or a lot of nothing. So we would say that at this moment, right at 10 to the minus 43rd seconds, let's say that all the four forces are unified into what we call a single superforce, and you'll find that this is actually something that's talked about in the literature. No matter where you go bounce around, it seems to be it is the current paradigm that there should eventually be a quantum theory of gravity. So all of them would be formed together into one big concept called the Planck Epoch. And the Planck Epoch is up until 10 to the minus 43rd seconds. So why would we have this concept of 10 to the minus 43rd seconds? Because that's the time when we expect the size of the universe to be about the size of a wave packet of the particles that would have existed at that time. That's a wild thought. And so the Planck time is where we combine, say, h bar, which is characteristic of a Planck of a quantum effect on wave size scales, and g is the Newton's gravitational constant, and c to the fifth power is the speed of light. So g indicates we're talking about the gravitation, and h bar represents we're talking about quantum effects, such as, remember the energy of a photon is h bar times the frequency, gives you the energy of a photon. So if we then say h bar times g over c to the fifth, which is a space-time measurement frequency sort of thing, and then take a square root of that, we get a time. And that time is 5.391 times 10 to the minus 44th seconds. That's the Planck time. And at that time, the wave packet size of the universe, remember we talked about the wave size of electrons and the wave size of photons? Now we can say the wave particle size of the entire universe would be this thing, so the size of the universe would be about the same size as a wave packet inside it. That would be the top Planck time. So how big was the universe at the Planck time? Well, it wasn't very big. So if we take the speed of light, which is the time that it would take for information to travel across that universe, it's not very big. It's about 1.6 times 10 to the minus 35th meters, which is really tiny, called the Planck length. And the Planck length is just simply equal to the speed of light times the Planck time. So nothing can get information across the universe faster than the speed of light at the Planck time. So the distance that light can travel in a Planck time is 1.6 times 10 to the minus 35th meters. And that would be the size of the universe at that time. All right. At that time, we would call it the Grand Unification Epoch. So at 10 to the minus 43rd seconds, the temperature is a staggering high, 10 to the 32nd Kelvin. And at that moment, that's when the gravity would separate from the superforce. So the end of the Planck era instantiates the grand unification epoch, where gravity then separates away and the strong and electroweak forces are still unified together as the grand unified theories force. So then there are two forces ruling all of physics inside of this very short time, early universe time, gravity and the grand unified theories. At this time, the universe is just very hot, as you can see by the temperature, and very, very, very dense. And the only thing that exists are quarks, antiquarks, proton, and photons. And they're all in equilibrium, meaning they all have the same temperature. They all have, because they're interacting inside of the universe. And as they are interacting, they get to be the same temperature. And that was key to an earlier concept. However, not long after, at a time of 10 to the minus 35th seconds, or 10 to the 8th Planck times later, the temperature drops to 10 to the 27th Kelvin. The strong force now separates from the grand unified force, which then is the end by the end of this time, from there to there, they have separated out, and the electromagnetic force and the weak forces remains unified. So at the start of the grand unified theory time, you have the separation of gravity from the gut objects, and by the end it has done. There's a rapid separation. That triggers some strange rapid inflation of the cosmos. All right, so then this is what we mean by the inflationary epoch. So the Planck epoch has everything bound together. During the grand unified theory epoch, or the gut epoch, then the gravity separates from the grand unified force to make two forces and some quarks and photons and photons, which are kind of like photons with electroweak photons is probably the best way of thinking about it. And then that's what exists in the universe. During that time, the universe expanded about 10 to the 43rd in size. The size scale A went big, really big. At that time, then the cosmic microwave background gets smooth, everything gets shoved apart, and at the end of that it stops. So let's see what this is all about. So during the inflationary epoch, there was nothing else there was something that dominated all the other components of the rate of expansion, and that was something like the dark energy component. Curvature, radiation, and normal matter didn't really matter for the energy density of the cosmos. It was just something that pushed the cosmos apart between 10 to the minus 36th and 10 to the minus 34th seconds. That pushed the universe apart so that the scale factor at Tf, which is T finished, compared to the scale factor of Ti, which is T initial. And that's an exponential expansion, and it's the time times the Hubble time. It gets you about e to the 100 or so, which gets you about 10 to the 43rd times of an expansion. That's an enormous growth rate inside a staggeringly short period of time, and that's wild. Of course, that's much larger than the speed of light. Much, much larger. But space-time itself can expand at the speed of light because it's not a thing. So no thing can go faster than the speed of light, but space itself can because it's not a thing. Remember, we're no longer dealing with quantum gravity anymore. We're just dealing with space-time, and space-time can still expand at that space. And now it's doing its own thing based upon the energy density of the cosmos, which is some crazy energy that's pushing it apart, some inflationary epoch. So when the inflation stops at 10 to the minus 34th seconds, the universe is really cold and really empty. And that's caused by the decay of energy density called the inflationary epoch. And that creates new particles such as quarks and leptons and light. So that's what's created at the end. So it just really empties the heck out of everything. So by that time, 10 to the minus 32nd seconds, until 10 to the minus 12th seconds, which is a still short period of time, but very long for it from its perspective, if you're considering tiny steps. Then the temperature drops rapidly, and the electroweak then force separates into the electromagnetic and weak forces, and now they're all separate. And so all you have in terms of matter at this time are quarks, leptons, meaning like electrons and anti-electrons, such as they are, as well as muons and other objects in that tree. But now you have all four forces. Four normal forces are finally coming into existence: gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic force. Notice that we've broken the symmetry from going from one thing that is the same no matter how you look at it to four things which are different depending on their size scales and their strengths. So we have broken the symmetry of the cosmos as it cooled off. So now we can get separate photons. You can get matter and photons, and then all sorts of things can happen from that point. So how does this solve the problems of the early cosmos? So the cosmic inflationary epoch solves the flatness problem by expanding the universe. So imagine we have a balloon, and the ant is on the surface of a balloon, and the balloon might be, say, 10 centimeters in radius. So the ant can easily say, wow, this is a nice little curvy balloon. I can walk all around it and find all sorts of curvinesses and find a little place where people inflated the balloon that I'm walking around on. But now, instead of kicking the ant off, we inflate the balloon extraordinarily rapidly until it's 10 to the 48th meters in size. Well, the ant's never going to see the curvature. The curvature is so incredibly large now that the ant's going to say, this is perfectly flat. Or if it's not flat, it's really close to flat, and I can't measure the curvature of it. So the radius of the balloon now is 10 to the 48th meters. He's never going to see it. So effectively, the inflationary epoch wipes out all curvature because the curvature now is so big that it's impossible to see inside your little world, which is the square box. It's impossible to see it. All right, so how does that work in terms of the numbers? Well, in terms of the numbers, we have the omega sub t that we saw at the beginning, which is the density compared to the critical density. It grows exponentially with time, and if we compare the final t sub final compared to t sub initial, which is the initial time, we would then pretend that even at the initial time, that there was a strong amount of curvature, really curved, really lumpy, such that the difference between them was about 1. So maybe it was twice as large as that. Maybe the curvature was huge. So it's pretty much the size, curvature was the size scale of the cosmos. In our ant analogy, the ant could be walking around on the surface of the balloon before it was inflated. It'd be very, very lumpy. So now inflated extraordinarily fast, and that goes up to e to the curvature then drops by a factor of 10 to the 87th. And that's so incredibly large that there's no way that we'll never actually be able to see any curvature. That allows for a lot of things to happen. So the flatness doesn't go away. In fact, as the universe expands for 13 billion years. Why not? Because it's just too big. The curvature is simply so large that there's no way for it to ever catch up. So the tiny, tiny, tiny non-flatnesses that probably exist, that may have existed during the Planck Epoch and the Gut Epoch, those things may have occurred, but they were smoothed out incredibly rapidly by the inflationary epoch, and they can't grow fast enough. The lumps can't grow fast enough in order to be measured. Even to today, where we find the critical density the current density compared to the critical, which is omega sub naught, we find that to be equal to the critical density contributed by matter and the critical density and the density parameter contributed to it by dark energy. The sum of those things is equal to 1, to the best of our ability to measure. Now, it could be that the current best of our ability to measure means that it's 10 to the minus 16th because the universe has caught up a little bit to the inflationary epoch, which we expect it to have done, as we see here. So in the early universe, before the inflationary epoch, the universe was really tiny, 10 to the minus 35th meters or so. And so everything inside of there can be the same temperature. Then it blows up rapidly. All that tiny thing that's all at the same temperature blows up huge. However, remember, the speed of light is finite and much smaller than the rate at which the universe grew. So light can only get to you from a place that's deeply embedded inside this newly large area. So now it's really big, everything's at the same temperature. There's practically nothing in it, but that's beside the point. And so everything's been cooled off, everything's been made to almost temperature of practically 0, and then you get more heating and stuff later. But the universe now becomes all the same temperature, all at the same time. And eventually the universe's horizon that we see starts to catch up to the boundary of the rate of expansion of the universe. So there's two horizons, right? So this solves the horizon problem. The horizon problem is solved because now everything's the same temperature inside a really big volume, and we just our horizon then grows because of the age of the cosmos. The horizon now we see is about 13 billion light years in every direction, about 14 billion light years in every direction. So now we have 2 points on opposite sides of the sky that can be seen to be the same temperature because a long time ago they were, but then they got shoved very far apart, and now we're just getting the light from them today. And that's what we mean by that dashed line in the third one over to the right. We're finally seeing the light from them today because that light now is just getting to us, and it has the same temperature. All the other particles of light have either gone by us or not yet gotten to us from outside of there because the universe, the horizon is not yet expanded for us to get to them. And by expanded horizon, I mean the universe has to have a certain age for that light to get to us from there. That's what we mean by the dashed line. That's where the universe has had a chance to get for light to get to us from there. So these points, A and B, were in thermal contact, then they got shoved really far apart, and now we're finally seeing them after we can find that the light from them is now finally reaching us after they emitted it 13.6 billion years ago. All right. The inflationary epoch also solves the monopole problem in a rather normal way because we would say the universe expands exponentially, so it became 10 to the 43rd times larger, but then the number density goes as that size cubed. So now the number density dropped off like e to the 300, so we would expect after the grand unified theory epoch, if there were 10 to the 82nd, that's a huge number. If there were 10 to the 82nds per cubic meter formed in the gut epoch, just at the beginning of the inflationary epoch, then after inflation, there would be 15 per cubic parsec. And then the universe expands and expands and expands and pushes them farther and farther and farther apart. So now we would expect only one in 1.1 times 10 to the minus 61 monopoles per cubic megaparsec. So basically the universe is expanded such that they're all so far apart that we'll never see any one of them. And the chances for us of having one inside of our horizon are practically zero. So we shouldn't expect any of them in the universe at all. Even if 10 to the 82nd were formed, we won't see any. If we did see one, it'd be one big thing, and we'd probably notice it. And if there were many formed, we would really be noticing them and people would be talking about them. But the fact that nobody talks about, oh, today we have a bad magnetic monopole day, so don't go outside today without your jacket, that doesn't happen. So since that doesn't happen, there's almost none in the universe, and for that, because the universe, even if it did form them, they're all really far away. So how did it do that? Well, the universe at that time, prior to that epoch, was in a state what we call a false vacuum state, meaning it had energy. So the Planck Epoch universe itself had a certain amount of energy associated with being itself. But that's a false state. There's nothing in it. So it's a vacuum of space-time stuff. And if there was a strong enough another strong enough hit, then it would push over that hump and then drop from the false vacuum state to a true vacuum state and release that energy. It is that releasing of the energy that creates the inflationary epoch itself, going over that hump with a big enough bump and then oscillating at the bottom like a little ball rolling backwards and forwards at the bottom of the true vacuum state in order to get that. And that so we can think of it as being supercooled. Just if you Google supercooled water, what I'm showing here is water that's been supercooled. So as you pour the water out, it actually freezes as it hits something. So the water is super cold. It's colder than ice. So if it hits any kind of thing upon which it can nucleate and form ice, it goes instantaneously from a water state to a liquid, to a solid state. That's the same thing as this. It's been super cooled, or the universe has been put into a false state of liquid. So all you need is a perturbation, a little lump, a little bump to push it over into the true state that it should be in, which is less energy. And when it does that, it releases that energy in the form of heat. And that's what you get. So what does that heat do? That heat creates bubbles. So as the universe bubbles and bubbles, these during the inflationary epoch, as it rolls around, as it tries to come to a stop, and the energy of the inflationary epoch uh, is effected into the cosmos, the energy that gets released as it bumps back and forth along close to the true vacuum releases energy in the form of particles and perturbations. Those perturbations then are dragged larger and larger by the expansion of the cosmos. And that's what this graphic is showing you, is that each of the perturbations, which is a lump of space-time that is growing, creates little pockets of energy density or mass density in the grand unified epoch. And they grow and grow and grow and grow. And the energy density of those perturbations then can be modeled. And as we model them, we find that, okay, from our viewpoint on the very right-hand side, when the very is today, we look back in time and we see on the two red lines where the cosmic microwave background should be viewed, the two opposite the sky lines have the same temperature. And the reason they have the same temperature is because the thing in the middle has the same temperature. And so each size scale gets smaller and smaller and smaller of angular difference between them. And so we can then look at that as our resolution of looking at the Planck probe, meaning we had some really tiny thing on the left-hand side. It exponentially expanded and then grew normally, and the horizon eventually caught up to it. But the middle band is the horizon crossing, which is when we actually see the objects, when we actually see the lumps and bumps. So those arrows that are called horizon crossings are when the lumps and bumps are moving back and forth across the cosmic microwave background. So the cosmic microwave background imprints the data of the early Planck epoch. And this exact set of patterns, the statistical analysis of the cosmic microwave background, is the shape of how much intensity or power there is at different angular frequencies or angular sized separations in the sky. That is determined, or at least there's a predicted thing that comes about from what I described before, which is the inflationary epoch occurred. There were little lumps and bumps that occurred during the inflationary epoch. They all were forced apart and forced to grow exponentially as they grew. And then once the universe stopped growing exponentially and all that latent heat of the false vacuum is done, then those perturbations, which were random and forced to become, they forced to grow exponentially, that will create lumps and bumps and waves in the early epoch of the energy distribution of the cosmos. And those will provide tiny anisotropies that will then grow. And when they grow, they will grow to a certain size. And when the universe is 350,000 years old at the time of the cosmic microwave background, and the appearance of the cosmic microwave background that we see in the sky is directly consistent, is completely consistent with that interpretation being the inflationary epoch did occur. So then let's hunt for it specifically. What are some other things that could have done? So the actually hunting for the signs of the inflationary epoch in the cosmic microwave background, and this is a team down in Antarctica that looked at with a microwave telescope called the Bicep 2 crew. And they were looking at specifically for cosmic microwave background to see if they can see a particular signal from it. Now, in the cosmic microwave background, there are two ways that light can be polarized. And we can see that the electrons in the top one, if they're density waves, the electron gets kind of shoved back and forth. And so it'll be shoved either towards you or away from you, and you get this E-mold polarization, which is very standard, and you find that in the cosmic microwave background. However, if there's a gravitational wave, then the electron gets squeezed and stretched. And as it gets squeezed and stretched, its electromagnetic field gets squeezed and stretched. And that changes the polarization of the light into what we call a B mode, or a kind of a curlicue mode, or something that has curls to it, like rotational. The E mode is just back and forth or up and down, but the B mode is rotational, and such gravitational waves should occur in the early cosmos due to the inflationary epoch. And this was their signal that that they claimed, which was anomalous because they did not take into account the foreground Milky Way, but we can certainly see the attempt to show the curlicueness of that. Unfortunately, this can also be masked by the Milky Way doing the same thing. But this was an anomalous paper that came about, and they had to retract it later. But in any event, if once we model the nature of the Milky Way and go look for really clean areas of the sky that don't have that, or at least know exactly how the foreground Milky Way affects the background, then maybe we can see it. Maybe the B mode signal can be seen. And that would have occurred during the Planck Epoch. So if you can get this, you're actually looking at the inflationary epoch. That's a big, 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 big thing. So a current research topic to do is to create a polarized map of the Milky Way so that it can be subtracted from the cosmic microwave background to find this signal in truth. And that's what we mean by it. There's the different kinds of polarizations that we have. Okay, so inflationary epoch solves the major things. It solves the flatness problem, it solves the horizon problem, and it solves the magnetic monopole problem. There is observational evidence for it, and there are observational tests for it. Finally, then we ask, what about the beginning? The Planck epoch is a time. What about time equals zero? What about the absolute beginning of the universe? The Planck epoch would be a time, and there wouldn't even be this thing called time, because space-time and gravity, which defines this nature of length and time and space, doesn't even exist yet as a thing. All there would be during the Planck epoch would be essentially black holes, wormholes, white holes. Space-time itself as a concept doesn't even exist. It's quantum space-time, so we don't even have a concept called space-time yet. So quantum gravity means there is no such thing yet as space-time, which is really weird. So how can you talk about time when you don't even have a thing called time yet? So it would be this perfectly chaotic, purely symmetric, unchanging, because there's no time, pseudo-meta-uber epoch, where everything is just these wormholes and black holes, and it's incredibly small, incredibly high density, and eventually some perturbation breaks off to form the rest of the cosmos. If there's a tiny, tiny, tiny phase state, then there would be a tiny change and then accumulation of some wibbly-wobbly, timey-wimey stuff, and then you go off you go to the gut era, and gravity breaks away, and boom, and all of a sudden everything occurs. Prior to that, there wasn't even a thing called time, so we really don't even know if there is a thing called time, or even if the time equals zero as a concept even has any meaning. That's a very strange thought, to think that there was no thing called time, so we can't even say that time equals zero is a thing, because we have to start from a time equals first step, which is a weird thought, the first step being the Planck time. So once there is a time, then the first time is the first 10 to the minus 43rd seconds of time. It's more like to say it's all a mess, and then the first step occurs. So the first step is a breaking of symmetry such that time exists. That would be the first step. A breaking of symmetry such that time exists. So you can even think of it backwards and forwards in time. It doesn't even matter. There is no such thing as time yet. So once you do that, you break time, you break the symmetry, time begins, and then you get the Planck epoch. Prior to that Planck epoch, nothing we can speculate. There's some quantum gravity. We don't know what this is, but it can't look anything. General relativity must break down, because general relativity can't really apply on the quantum size scales. It must be something like that. So people really think that there must be something like quantum gravity, and that space-time itself becomes unified with the other forces in some weird way, and space-time as an object itself must go away on the highest time scales. On the smallest time scales, the highest energies and the highest densities. However, nobody has a quantum theory of gravity at this time, so nobody can really answer it. And therefore, a lot of things are happening inside that first minute of the Big Bang. You have the quantum epoch. You have the earliest times when it was just this supergravity, space gravity, timey-wimey, stuffy fluff prior to 10 to the minus 43rd seconds. And then gravity breaks away from the grand unified epoch. You have the inflationary epoch. That then occurs up until 10 to minus 36 seconds, and during that time you have like crazy black hole-y type things that are creating perturbations. They then separate out after the inflationary epoch and reheat the universe to make a light and photons and leptons and so forth. And then the electroweak breaks away, and you have matter and so forth breaking apart. Eventually, by about a minute or so, you have simplified down to protons and neutrons and electrons and photons and neutrinos and things like that. And you finally have four forces once just before you get to a second, and then you can actually form normal matter. So a lot of things happen inside the first second of the cosmos, and we have a lot of knowledge down to the idea of what we think is happening inside the first second. Much of the ideas that I talked about what the first second are the source of incredible research, but the picture is probably pretty good. It just needs to be fleshed out more, and the hard part is to actually get observational evidence, and hopefully B-mode cosmic signals inside of the cosmic microwave background can show that. However, the cosmic microwave background itself shows evidence in terms of that the inflationary epoch, if not correct, then something an awful lot like it happened. So if the Big Bang did not occur, something really much like it did occur. And just to make a more simplified appearance, here it is. We have some crazy thing happening at the inflationary epoch, and when quantum fluctuations created the cosmos, there was a major afterglow of light from the universe from 350,000, 380,000 years after the Big Bang. Then light, there were no stars until about 400 million years after the Big Bang, when the first stars form, and then galaxies form, and then galaxy clusters and planets and other elements and heavier elements, and eventually we get us on the right-hand side. But the early cosmos, whatever happened in those first few moments, meaning 10 to the minus 36 moments, is imprinted on the cosmic microwave background. And detailed studies of that demonstrate that the Big Bang as a thing did occur, or if it didn't occur in the picture that we've been talking about in the last few lectures, if that didn't occur, then something almost identical to it did occur. And that's kind of it for the nature of the origin of the universe. All right, we'll see you soon.